Welcome to The Explainer. Today, we're going to look at the incredible forces that build the very architecture of our planet. Seriously, from the smallest hill to the most massive mountain range, there's a story written in stone. You just have to know how to read it. So let's just start with a really big question. We all see these majestic, crumpled mountain ranges, right? But we also know that the sedimentary rock they're made of was originally laid down in perfectly flat horizontal layers. So how do you get from flat to that?
Well, the answer lies deep inside the Earth. It's a story about these immense pressures we call tectonic forces. They're constantly, and I mean constantly, pushing, pulling, and twisting our planet's crust. These forces, which are powered by the incredible heat in Earth's core, are pretty much the master builders of our world.
Okay, so these colossal forces can basically be broken down into three main types. And these three are the engine behind literally every geological structure we see. Understanding them is, step one in learning the language of the rocks.
Think of it like this. Compressive forces, well, they squeeze. It's like pushing the ends of a rug together. Tensional forces stretch things out, kind of like pulling on a piece of taffy. And then you have shearing forces, which just slide things past each other, like when you slide your hands in opposite directions on a deck of cards. So the big question is, what happens when a rock is under this much stress? It doesn't just sit there, that's for sure. It deforms. But how it deforms is where things get interesting. It all depends on stuff like the temperature, the pressure around it, and what kind of rock it is in the first place.
Ultimately, it really just comes down to two basic outcomes. The rock can either bend, geologists call this plastic deformation, or it can break, which we call brittle deformation. This bend or break idea is absolutely crucial. Because when a rock bends, you get a fold, and when it breaks, you get a fault. So let's talk about that first response. What happens when rocks decide to bend instead of break? This is how some of the most spectacular landscapes on the entire planet are made. They form what we call folds. It's just like when you push a piece of cloth from both sides and it buckles. Rock layers do the exact same thing. They crumple into these amazing wave-like shapes. This is that ductile or plastic response of the Earth's crust to all that pressure. And this shows the two main types of folds perfectly. On the left, you've got an anticline, which arches up kind of like a capital A. And on the right is a syncline, which sinks down into a trough. Now, here's a little pro tip for geologists. If you imagine the top of that anticline getting worn away by erosion, the oldest rock layers would be exposed right in the middle. For the syncline, it's the total opposite. The youngest rocks are tucked away safely in its core. And the scale of these things, it's just astounding. I mean, they can be these tiny, microscopic wrinkles in a rock you could hold in your hand, or they can be massive, gigantic structures that form entire mountain ranges stretching for thousands of kilometers. But rocks can't bend forever. So what happens when the stress is just too much, or the rock is too cold and rigid? It shatters. This is the brittle response, and it creates these massive fractures in the Earth's crust that we call faults. So what exactly is a fault? It's not just a crack in the rock. A fault is a fracture where the blocks of rock on either side have actually moved. That movement, what geologists call displacement, that is the key defining feature. And just like with the stresses, we can classify faults too. The key is to look at what forces created them and which way the rocks moved. Each of those three tectonic forces we talked about creates its own unique type of fault. Let's break these down. Geologists have this simple little trick. The block of rock that's above the angled fault line is called the hanging wall. Now, in a normal fault, the kind caused by stretching, that hanging wall drops down. But in a reverse fault, which is caused by squeezing, that same hanging wall gets pushed up. And then you have the strike-slip fault, where the blocks just slide sideways past each other. No up or down movement at all. And it's this movement that causes earthquakes. For years, sometimes even centuries, stress just builds and builds along a fault. Then, when the friction can't hold it any longer, the rock suddenly breaks and slips, releasing all that stored-up energy in an instant as these incredibly powerful seismic waves. Look, understanding these folds and faults, it's not just some academic thing. It's about learning to read the language of the Earth. And this language tells us about our planet's past, but it also has some very real consequences for all of us today. This table really sums up the key differences. Check out that top row. Folds are all about plastic bending, while faults are about brittle breaking. And look at the primary force row. Folds are almost always from compression, but faults, they can be caused by any of the three forces. So by studying these features, geologists can basically act like detectives, piecing together these immense tectonic events from the past.
And this knowledge is super practical. The same folds that build mountains can also trap valuable stuff like oil and gas. Mapping out faults is absolutely critical for figuring out earthquake hazards in our cities. And you definitely want to know if you're building a massive dam or a tunnel on unstable ground, right? This is geology in action. It all kind of boils down to one of the most fundamental ideas in all of geology, summed up by this one phrase: the present is the key to the past. It just means that the slow, powerful forces shaping our planet right now are the very same ones that have been at it for billions of years, building the world we see all around us. So once you learn to read these structures, you start to see this epic story written in the rocks everywhere you look. The next time you pass a road cut or see a mountain cliff, take a closer look. Are the layers bent? Are they broken? What story is waiting to be discovered right there in your own backyard?